Good morning.
Good morning, sir.
Okay. How was the unit test? Unit test எப்படி எழுதுனீங்க? யூனிட் டெஸ்ட் எப்படி எழுதுனீங்க? கார்த்திபன் கார்த்திபன் இருக்கீங்களா? 11:45 ஆனாதான் உள்ள வர்றது, இல்லைன்னா ஜாயின் பண்ணி விட்டு எங்கேயாவது போயிடுறது. ஏன்டா? ஓகே, யூனிட் டெஸ்ட்ல ஏதாவது கொஸ்டின் டவுட் இருக்கா? ஒரு 5 கொஸ்டின்ஸ் கேட்டிருந்தேன் இல்லையா? அந்த 5 கொஸ்டின்ல ஏதாவது டவுட் இருக்கா யாருக்காவது? Okay, என்ன கொஸ்டின் கேட்டிருந்தேன்? ரைட் த நெசசிட்டி ஆஃப் மாடுலேஷன். மாடுலேஷனோட நெசசிட்டி விச் மீன்ஸ் ஒரு 6 பாயிண்ட் இருக்கும் இல்லையா? மாடுலேஷனோட நீட்ஸ். ஓகே, அது எழுதிருப்பீங்க. நீங்க எழுதுனீங்களா? Have you write those need for modulation or சும்மா நான் மட்டுமே பேசிட்டு இருக்கா? நான் கேட்கல. யாராவது ஒருத்தவங்க ரெஸ்பாண்ட் பண்ணுங்க. இல்ல do I
Sir,
need
Edma sir.
to mention anyone?
Yes, sir.
Okay, what is the
Sir.
modulation? What are the needs?
Reduction in antenna height,
Yes, very good.
long distance communication,
Yeah, good.
Ease of radiation.
multiplexing.
Okay, good. Reduction in antenna height, long distance communication, avoid mixing up of other signals, multiplexing,
Multiplexing.
ease of radiation, improve the quality of reception. இதில் ஏதாவது ஒரு 4 பாயிண்ட் எழுதியிருந்தாலும் யூ வில் பி அவாய்டட் வித் 2 மார்க்ஸ். நோ ப்ராப்ளம். ஓகே, 6 எழுதணும்னு அவசியம் இல்லை. 4 பாயிண்ட் எழுதியிருந்தாலேயும் இட் வில் பி ஓகே. இட்ஸ் ஓகே. தென் next question is give the diagrammatic representation. Give the diagrammatic representation of AM, PM and FM wave. அதுவும் ஒரே ஸ்லைடில் இருக்கும். ஜஸ்ட் யூ நீட் டு ட்ரா தி மெசேஜ் சிக்னல் அண்ட் ஏஎம் வேவ். சரிங்களா? ஒரு கரியர் சிக்னலோட ஏஎம் வேவ் எழுதிருப்பீங்க, வரைஞ்சிருப்போம். அதுக்கப்புறம் let me present that. என்ன விண்டோப்பா தெரியுது? நீட் ஃபார் மாடுலேஷன் தெரியுதா? இல்லை வேற ஏதாவது விண்டோ தெரியுதா?
மாடுலேஷன் தான் தெரியும்.
நீட் ஃபார் மாடுலேஷன் தெரியுதா? ஓகே, இந்த டயக்ராம் வரைஞ்சிருந்தீங்க அப்படின்னா யூ வில் பி அவார்டட் வித் 2 மார்க்ஸ். இந்த 3 டயக்ராம். சரிங்களா? இதுதான் என்னது? give the diagrammatic representation for of AM, FM and PM signals. ஓகேவா? Next question is modulation index. What is meant by modulation index? Modulation index is nothing but ratio between amplitudes of EM and FM wave. அதை மட்டும் நீங்க எழுதினா போதும். அதுக்கு ஒரு எக்ஸ்பிரஷன் இருக்கும், EM by EC அப்படின்ற ஒரு எக்ஸ்பிரஷன். அந்த எக்ஸ்பிரஷன் எழுதிருந்தீங்க அப்படின்னா you'll be awarded with 2 marks. இந்த எக்ஸ்பிரஷன் தான் M equal to EM by EC, the ratio of maximum amplitude of modulating signal to maximum amplitude of carrier signal is called modulation index. Okay, கொஸ்டின் மாடுலேஷன் இண்டெக்ஸ் மட்டும் கேட்டிருந்தானா இல்லை மாடுலேஷன் இண்டெக்ஸ் ஃபார் ஏஎம் அண்ட் எஃப்எம் வேவ். இது வந்து ஏஎம் வேவ். எஃப்எம் வேவோட மாடுலேஷன் இண்டெக்ஸ் என்னப்பா? அதுக்கு ஒரு மார்க் இருக்கும். எஃப்எம் வேவோட மாடுலேஷன் இண்டெக்ஸ் ஃபார் எஃப்எம் வேவ் ஈக்குவல் டு கே இன்டு இஎம் டிவைடட் பை ஒமேகா எம். இந்த எக்ஸ்பிரஷனுக்கு ஒரு மார்க். இஎம் பை இசிக்கு ஒரு மார்க்கு, கே இன்டு இஎம் டிவைடட் பை ஒமேகா எம்க்கு ஒரு மார்க். ஓகேவா? கண்டிப்பாக உங்களுக்கு யூனிவர்சிட்டி கொஸ்டினா இருக்கட்டும், யூனிவர்சிட்டி கொஸ்டின்ல இருந்தும் இந்த இது கண்டிப்பா இருக்கும். மாடுலேஷன் இண்டெக்ஸ் அப்படின்ற ஒரு கொஸ்டின் கண்டிப்பாக இருக்கும், இல்லாம இருக்காது. சரியா? எய்தர் ஏஎம் இருக்கலாம், இல்ல எஃப்எம் இருக்கலாம், இல்ல பிஎம் இருக்கலாம். இந்த 3 மாடுலேஷன் இண்டெக்ஸ்ல ஏதாவது ஒரு தியரி கொஸ்டின்ல இருக்கும். அப்படி இல்லை அப்படின்னா ப்ராப்ளம்ல வரும். அப்படி இல்லை 2 மார்க் ப்ராப்ளம்ல வரும். அப்படி இல்லைன்னா பார்ட் பில ப்ராப்ளம்னாலும் கண்டிப்பா மாடுலேஷன் இண்டெக்ஸ் இருக்கும். மாடுலேஷன் இண்டெக்ஸ் இல்லாம இருக்காது. ஓகே. The next question is find the carrier power. Hello.
சார் ஆக்சுவலி அந்த கொஸ்டின் பேப்பர்ல மாடுலேஷன் இண்டெக்ஸ் ஃபார் எஃப்எம் தானே சார் கேட்டிருந்தாங்க?
ஏஎம் அண்ட் எஃப்எம் ரெண்டுமே இருந்தது.
எஸ் சார். இப்போ வந்து பிஎம்க்கு தானே சார் கே இன்டு இஎம் ஈக்குவேஷன்.
கே இன்டு இஎம் வந்து பிஎம்க்கு, எஃப்எம்க்கு வந்து கே இன்டு இஎம் டிவைடட் பை ஒமேகா எம்.
அதுவும் அது மேக்ஸிமம் ஃப்ரீக்வன்சி டிவியேஷன் பை மாடுலேட்டிங் ஃப்ரீக்வன்சி அந்த ஈக்குவேஷனா சார்? டெல் பை எஃப்எம்.
யா, அது எழுதினாலும் கரெக்ட் தான். இல்ல மாடுலேஷன் இப்போ ஸ்கிரீன்ல தெரியும் பாருங்களேன், மாடுலேஷன் இண்டெக்ஸ் ஃபார் எஃப்எம் ஈக்குவல் டு கே இன்டு இஎம் டிவைடட் பை ஒமேகா எம்னு இருக்கு இல்லையா? இது எழுதினாலும் கரெக்ட் தான்.
ஓகே சார்.
புரிஞ்சதா? ரெண்டு எக்ஸ்பிரஷன்ல எந்த எக்ஸ்பிரஷன் எழுதினாலும் சரி கரெக்ட் தான், தப்பு கிடையாது. ஓகே.
ஓகே.
Your next question is find the carrier power of a AM broadcast transmitter that radius 20 kilowatt for which the modulation index is 0.6. I think we have solved that problem. ப்ராப்ளம் சால்வ் பண்ணிருப்போம்னு நினைக்கிறேன். கேரியர் பவர் கேட்டிருக்காங்க தானே? இது இல்லையா? ஓகே. ப்ராட்காஸ்ட் டிரான்ஸ்மிட்டர் வந்து 20 கிலோவாட் டிரான்ஸ்மிட் பண்ணிருக்கு. இங்க என்ன கேட்டிருக்காங்கன்னா கேரியர் பவர் கேட்டிருக்காங்க. மாடுலேஷன் இண்டெக்ஸ் கொடுத்துட்டாங்க. அப்போ என்ன பண்ணிக்கலாம், இந்த எக்ஸ்பிரஷன் மட்டும் நீங்க கால்குலேட் பண்ணா போதும். ஜஸ்ட் மாடுலேஷன் இண்டெக்ஸ் பதிலாக அங்க கொடுத்த வேல்யூ 0.6 போட்டீங்கன்னா போதும். ஓகேவா? சேம் ப்ராப்ளம், இதே ப்ராப்ளம் தான். டோட்டல் பவர் 20 கிலோவாட் கொடுத்துருக்காங்க. இங்க மாடுலேஷன் பெர்சன்டேஜ் வந்து 75 கொடுத்துருக்காங்க. அங்க என்ன கொடுத்துருக்காங்க, மாடுலேஷன் இண்டெக்ஸ் வந்து 0.6 கொடுத்துருக்காங்க. தட்ஸ் த சிம்பிள் டிஃபரன்ஸ். ஓகேவா? The next find the bandwidth of an AM DSB FC. bandwidth கேட்டிருக்காங்கப்பா. AM ல bandwidth என்னப்பா? AM ஓட bandwidth எப்படி கால்குலேட் பண்ணுவீங்க?
2FM.
சிம்பிள். bandwidth is given by 2 into FM. இது வந்து frequency இல்லையா? ஓகே. இப்போ FM ஓட சிக்னல் என்ன கொடுத்துருக்காங்க? FM frequency கொடுத்துருக்காங்களா? bandwidth is given by 2 FM and here FM is given as 5 kilohertz. அப்ப என்ன இருக்கும், 2 into 5 kilohertz. bandwidth of an AM DSB FC is 10 kilohertz. அவ்வளவுதான். ஓகேவா? the next வந்து இந்த ப்ராப்ளம் நம்ம ஆல்ரெடி டிஸ்கஸ் பண்ணிருக்கோம். நம்ம அதே ப்ராப்ளம் தான். அப்பர் அண்ட் லோவர் சைட் ஃப்ரீக்வன்சிஸ் வேல்யூ கூட மாத்தலாம் நினைக்கிறேன். அதே ப்ராப்ளம் தான். இந்த கொஸ்டின் தானே? I think it's the question asked 500 kilohertz. ஓகே. இந்த கொஸ்டின் தான் கேட்டிருக்காங்க. இதுல இதே ஸ்டெப்ஸ் நீங்க ஃபாலோ பண்ணா போதும். அப்பர் அண்ட் லோவர் சைட் பேண்ட் ஃப்ரீக்வன்சிஸ் கேட்டிருக்காங்க. FM FC இருக்கு. therefore you can find the FM and USB and LSB with FM and FC value. For LSB FC minus FM. For USB you need to find FC plus FM. Modulation coefficient என்றப்போ EM divided by EC. EM ஓட வேல்யூ என்னது? 0.75. சரி 7.5 and EC ஓட வேல்யூ 20. அப்போ EM by EC போட்டுடலாம். நீங்க போட்டுடலாம்ல? ஓகே. மாடுலேஷன் இண்டெக்ஸ் EM by EC சப்ஸ்டிட் பண்ணிரலாம். தென் அடுத்து என்ன கேட்டிருக்காங்க? percentage மாடுலேஷன் கேட்டிருக்காங்க. மாடுலேஷன் percentage மாடுலேஷன்னா மாடுலேஷன் கோஎஃபிஷியன்ட் வர்ற வேல்யூ இன்டு 100 தான் percent மாடுலேஷன். The next is peak amplitude of the modulated carrier upper and lower side frequency voltages. peak amplitude கேட்டிருக்காங்கப்பா. peak amplitude எப்படி போடுவீங்க நீங்க? amplitude of carrier தான் peak amplitude. இது அப்படியே டைரக்டா போட்டுக்கலாம். கேரியர் வந்து 20 வோல்ட் தான் கொடுத்துருக்காங்க. therefore amplitude of a modulated carrier is 20 volt. amplitude of LSB is given by MEC by 2. அப்போ m ஓட வேல்யூ நம்ம கால்குலேட் பண்ணிருப்போம், போன ஸ்டெப்ல கால்குலேட் பண்ணிருப்போம். EC is given as to 20 divided by 2. சேம் வேல்யூ தான் USB க்கு இருக்கும். And next question is, next topic is maximum and minimum amplitudes of the envelope. Maximum and minimum amplitude கேட்டிருக்காங்க. Maximum amplitude is given by EC plus EM and minimum amplitude is given by Emax minus 2EM. First, to find the Emin, you need to find the value of Emax. அப்போ Emax என்ன போடுவீங்க? 27. EC plus EM calculate பண்ணுவீங்க நீங்க. EC is given as 20 and EM is given by 7.5. then ரெண்டையுமே calculate பண்ணிக்கலாம். then Emin க்கு இந்த ஃபார்முலா வச்சு you can calculate the value of E minimum. Okay, அதுதான் first 8 மார்க்குக்கு. then with the help of frequency spectral diagram differentiate 5 types of SSB signals. 5 types of SSB signals இருக்கு இல்லையா? அந்த 5 types என்னென்னப்பா? just SSB FC னா என்னன்னு எழுதுனா போதும். எழுதி இந்த 4 பாயிண்ட் எழுதி இந்த டயக்ராம். then SSB SC க்கு இந்த பாயிண்ட்ஸ் then diagram. then SSB RC ISB then VSB. ஓகே, மொத்தமே இருக்கிறது 5 டைப் தான். யாரோ ஒருத்தவங்க கேட்டிருக்கீங்க 5 டைப் எழுதுனா போதுமான்னு வேற கேட்டிருக்கீங்க நீங்க.
சார் அது நான் தான் சார் கேட்டேன்.
நீங்க தான் கேட்டீங்களா?
சார் ஆனா டயக்ராம் வரையவே இல்லை சார். சார் டயக்ராம் வரையல சார். ஆனா
ஓகே, வித் தி டயகிராமேட்டிக் தான கேட்டிருக்காங்க क्वेश्चनல. with the help of frequency spectral diagram. சரிங்களா? frequency spectral diagram முக்கியம். 2
அதான் சார் கேட்டேன்.
3 மார்க் இருக்கும். very important. whenever diagrammatic represent because நீங்க டயக்ராம் வந்து சில பேர் என்ன பண்ணிருப்பீங்க அப்படின்னா ஆன்சர்ஸ் மட்டும் எழுதிட்டு டயக்ராம லாஸ்டா வரைஞ்சிக்கலாம் அப்படின்னு சொல்லி விட்டுருவீங்க நீங்க. அப்ப என்ன ஆகும்? டயக்ராம் லாஸ்ட்ல டைம் இருக்காது அப்படின்றதுனால கொசன் வரைஞ்சிருவீங்க நீங்க. அந்த மாதிரி இருக்கக்கூடாது. எப்பயுமே டயக்ராம்க்கு ஈக்குவல் வெயிட்டேஜ் இருக்கும். 7 மார்க் கொஸ்டின்ல கண்டிப்பா அட்லீஸ்ட் ஒரு 40% ஆஃப் த மார்க்காவது டயக்ராம் கொடுப்பாங்க. அப்ப ஃபர்ஸ்ட் நீங்க வரைய வேண்டியது, ப்ரியாரிட்டி கொடுக்க வேண்டியது டயக்ராம்க்கு. டயக்ராம் நீங்க ஒழுங்கா வரைஞ்சிருந்தீங்க அப்படின்னா அதை வச்சு ஈஸியா நீங்க தியரி எழுதிடலாம். ஸோ டயக்ராமுக்கு ஹை ப்ரியாரிட்டி கொடுக்க பாருங்க. டயக்ராம் நல்லா இருந்தாலும் தியரி மார்க் ஈஸியா வரும் தியரிக்கு. அதனால கொஸ்டின் ஆன்சர் எழுதி முடிச்சுட்டு டயக்ராமுக்கு கேப் விட்டுட்டு கடைசியில் டயக்ராம் வரைஞ்சிக்கலாம் அப்படின்லாம் எதுவுமே இனிமேல் எந்த சப்ஜெக்ட்டுக்குமே சரி அந்த மாதிரி திங்க் பண்ண வேணாம். ஓகேவா? ஓகே, நவ் shall we start the next unit? Sorry, next topic. Shall we? In the last class we have seen pulse code modulation. Am I right?
Yes sir.
Okay, we have clearly seen the generation method of pulse code modulation in the last class, and we have also seen the natural sampling and flat top sampling. Okay, am I right? And at last we have seen dynamic range and coding efficiency. Okay, dynamic range is nothing but ratio between maximum amplitude to the minimum amplitude. In the 3-bit PCM code, maximum amplitude is +3 volt and minimum amplitude is -3 volt. Therefore, ratio between these two gives the value of dynamic range. Okay. The next is a coding efficiency. Coding efficiency is nothing but total number of bits that a device can be generated to the ratio between number of bits required to transmit a signal. Okay, coding efficiency is given by the ratio between number of bits that is required to generate a PCM code for the signal to the total number of bits that can be generated by that device. This n min is nothing but total number of bits required by that particular PCM, okay, or by that particular signal. But this n represents the total number of bits or the total capacity of a device that generates a possible number of bits. For example, if I am using a device that is generating 8-bit code, okay, therefore n is given by 8, capital N is 8, but for a particular signal it is enough to use only 5 bits. Okay, for a particular signal, if it is enough to use only 5 bits, then n mean is represented by 5. 5 by 8 into 100 is nothing but coding efficiency of that device. Okay, is it clear? Okay, now let's see PAM. Okay, PAM is nothing but pulse amplitude modulation. It is similar to the amplitude modulation which was discussed in the first unit. In the first unit we have discussed amplitude modulation, and the same thing is applicable here except the carrier wave. Okay, in the first unit we have chosen carrier as an analog signal, but here we are choosing carrier as a pulse signal. Okay, instead of an analog signal we are choosing a pulse signal to carry our original message signal. Here the amplitude of the pulse, okay, in the slide itself it is given clearly. The amplitude of a carrier pulse is varied proportional to the amplitude of message signal. Okay, here in the diagram it is a pulse. Okay, and we have seen that as a carrier wave, the amplitude of the pulse doesn't get changes. Pulse remains uniform. Okay, the amplitude of the pulse is uniform. There will be no change in the pulse when we are choosing that as a carrier wave. Okay, but whenever the message signal get varies, the amplitude of the pulse gets varied in the pulse amplitude modulated wave. Is it clear? See this figure. It is a pulse amplitude modulated wave. Here, instead of maintaining the amplitude of the pulse, the amplitude of the pulse gets varied based on the message signal. Here the message signal amplitude gets increases, so the amplitude of the pulse is also increases, and after a particular duration the amplitude of the message signal gets decreases. Okay, and up to this point the amplitude of the message signal is decreases, therefore the pulse amplitude is also decreases, and after this the amplitude of the message signal once again starts increasing, therefore the amplitude of the pulse signal is also increasing. Okay, it is a pulse amplitude modulated wave because the position or the width of the pulse doesn't get changes, only the amplitude of the pulse gets changes based on the message signal. That is very important. Whenever the amplitude of the message signal increases, the amplitude of the pulse signal also increases, and once the amplitude of the message signal gets decreasing, the amplitude of the pulse signal is also gets decreases. Is it clear? Am I clear to you? Okay, and
sir.
next is given as a pulse amplitude modulator. Okay, this modulator is nothing but a circuit that generates this resultant waveform. Okay, this simple circuit produces the pulse amplitude modulated wave, and here we are using a multiplier. A simple multiplier is used in the PAM modulator. Okay, and one input of a multiplier is a message signal, and that message signal carries the information that is used for that has to be transmitted over a particular distance. Okay, then another input of a modulator is a pulse signal, and this pulse signal acts as a carrier wave. Okay, modulator has modulator or a multiplier. Okay, we can call simply call this as a multiplier. Multiplier has two inputs. One input is the message signal and other input is a carrier pulse. Okay, and the output of a modulator is a PAM signal. Just the amplitude of the message signal is multiplied with the amplitude of pulse signal. The basic functionality performed here is based on the whenever simply we can say that the amplitude of the message signal gets added or subtracted with the amplitude of pulse signal. Is it clear? Okay, let's consider here in the first instant or in the first sampling, the amplitude of a basic pulse is 5 volt. Okay, this 5 volt remains constant for any pulses. This okay. Here let's consider this diagram. Here the let's assume the amplitude of the pulse is 5 volt. Okay, therefore in the first sampling the amplitude of the pulse is 5 volt, second sampling is also the amplitude of the pulse is 5 volt, and the third and fourth also remains same in case of a carrier pulse. Okay, let's assume the message signal varies between 0, 5 volt, 0, minus 5 volt. Let's assume. Okay, the voltage may gets differ based on our requirement or based on the message signal, the voltage may differ, but for our assumption let's assume the message signal varies between 0, 5, 0, minus 5, and once again it goes to 0. Okay, and in the first sampling here the amplitude of the pulse is 5 volt, and here the amplitude of the message signal is 0. Okay, therefore 5 plus 0 it gives 5 volt. Okay, and here the amplitude of the pulse is 5 volt, and here the amplitude of the message signal is 5 volt, then 5 plus 5, 10 volt. Okay, here the amplitude of the pulse is 10 volt, and here the amplitude of the message signal is 0, and the amplitude of the pulse is 5, therefore 5 plus 0, once again 5, and here the amplitude of the pulse is 5, and amplitude of the message signal is minus 5, 5 minus 5, 0. The amplitude of this pulse signal must be 0. Okay, for my assumption I have assumed this as a 5 and 5 volt. Okay, the actual scenario may be varied, which means the amplitude of the pulse may be higher. The amplitude of the pulse may be 8 volt or 10 volt. The signal can range from 0, 5, 0, 5, 0. Okay, there isn't any constraint that the amplitude of the message signal, the amplitude of the pulse signal should be same. Am I clear? You may ask, here the amplitude of the pulse signal is 5, and here the amplitude of the message signal is minus 5. Therefore 5 minus 5, it has to be 0. But here they have given some peak signal. Is it clear why they have given some peak signal? Because the amplitude of the pulse may be higher than that of message signal. Purinjadappa, is it clear?
Yes, sir.
Okay. Okay. Now let's see the basic pulse amplitude modulator. Okay. First, before transmitting our message signal into any modulator or any multiplier, we need to check whether the message signal lies within a particular band, particular frequency band. Okay, for that we are transmitting our message signal into a low pass filter. Okay, before transmitting our message signal into a multiplier, we are transmitting our message signal into a low pass filter. As I have shown that message signal frequency should not get increased beyond a particular value. Okay, for that we are using low pass filter, because some of the high frequency component may be added with the original information source, that is unwanted noise. To filter that unwanted noise, we are filtering that high frequency components. That function is performed by low pass filter, and in the last class itself I have clearly explained the function of low pass filter. Low pass filter will be having one higher cutoff frequency, and it will not allow the frequency which has higher than that of that cutoff frequency. Okay, the signal which has a frequency higher than that of cutoff frequency will be filtered. That is the function of low pass filter. Okay, that is the thing it is stated here. Low pass filter, LPF means low pass filter. Low pass filter performs band limiting operation. All the filter performs band limiting operation. All the filters, which means a low pass filter or high pass filter or band pass filter, all the filter performs the band limiting operation. Based on our requirement, we can choose whether we need to send the whether we need to use a low pass filter or band pass filter or high pass filter. In the PCM we have used band pass filter, and here we need low pass filter, because in the message signal high frequency component should be eliminated, because our original message signal will be of low frequency. Okay, therefore high frequency component is nothing but an unwanted noise, so it has to be removed. So we are using low pass filter. Okay, then the output of a low pass filter is transmitted to the multiplier, and here multiplier in PAM, this multiplier operation is performed by a balanced modulator. Okay, or this multiplier is also called as a balanced modulator. That is the thing that that is the device which will be utilized in the PAM modulator. Balanced modulator is nothing but a device which accepts both message signal and pulse signal, or which accepts both the input at same time, and it combines both the signal at same ratio. Okay, or it performs the operation between both the signals at same ratio. That is nothing but a balanced modulator. Okay, and this output of this balanced modulator is a PAM signal, and I have clearly explained the operation involved in the multiplier. That is, it actually sums the amplitude of message signal and pulse signal. Okay, is it clear? It is the basic operation of a PAM modulator, and the generation of PAM modulator can be explained or can be obtained with a simple multiplier circuit. Okay, next is a bandwidth required for a transmission of PAM signal. Okay, and by sampling theorem or a Nyquist sampling theorem, we know that a sampling rate, this sampling rate is nothing but Fs. Fs must be greater than or equal to 2 into Fm. Okay, we have seen the sampling theorem. Okay, in the first class itself we have seen the sampling theorem, and the basic criteria for an efficient transmission of a PAM signal must be, or any signal, okay, must satisfy this condition, because all the modulation are performed after sampling. Okay, to perform efficient sampling, this criteria must be satisfied. Okay, therefore whatever may be the modulation technique we choose, we may choose PAM, PWM, PPM, or PCM, but first this condition must be satisfied. That is, sampling rate must be greater than or equal to twice the message signal frequency. Okay, and TS is nothing but sampling period. Okay, sampling rate and sampling period can be related by inverse of each other. Okay, sampling rate and sampling period are inverse of each other. I think you might have remembered that. Okay, sampling rate, Fs is nothing but sampling rate, Ts is nothing but sampling period. It is related with Fs is equal to 1 by Ts, and here we have Fs must be greater than or equal to 2Fm. Therefore, Ts must be less than or equal to 1 divided by 2Fm. Okay, Ts, to take Ts, we need to take the reciprocal. Whenever we take the reciprocal, this symbol gets interchanged. Okay. Okay, therefore Ts must be less than or equal to 1 divided by 2m. This tau is nothing but on time of a pulse. Tau is denoted by on time. Ts is nothing but total period of a pulse. You need to note the difference between Ts and tau. Okay, here tau is nothing but, or small t is nothing but the on time of a pulse. This on time is represented by tau, or off time. On time or off time, both are represented as tau, because total sampling period Ts is given by the summation of on time and off time. Okay, the on time of a pulse is given by tau on. The off time of a pulse is given by tau off. Here I have mentioned T on and Tf. Okay, for notation I have used T, and here to introduce the differences I have used tau here. Okay, since sampling period is the sum of on time and off time. Okay, therefore this tau must be less than Ts. Is it clear? Sampling period is the summation of on time and off time. Here tau represents either off time or on time. It represents only one time. It may be on time or off time. Okay, instead of this Ts is given by summation of on time and off time. Here we are using tau to represent either on time or off time. Therefore, the on time must be lesser than or equal to must be less than, not lesser than equal to, the on time must be less than total time, and also off time must be less than total time. Is it clear? Puridapa? Why we have used this condition? Because tau represents either on time or off time. It doesn't represent both. But TS represents the summation of on time and off time. Okay? 5 plus 3 equal to 8. Okay, if tau denotes 5, it must be less than 8. Or if tau denotes 3, it also must be less than 8. That is the condition given here. Okay, tau must be less than TS. Okay, and F max is nothing but maximum frequency of a pulse. Okay, the maximum frequency of a pulse will be occurred whenever the on time and off time is equal. Okay, whenever the on time and off time of a pulse is equal, or whenever a pulse has same on time and same off time, we can call that a pulse has maximum frequency. Okay, so that is given as F max equal to 1 divided by 2 tau. Okay, and this 2 tau, how this 2 tau came? We know the, wait a minute. Okay, if T on equal to tau, and T off is also equal to tau, then T total or TS will be equal to 2 tau. Okay, is it clear? If T on equal to tau, if whenever a pulse has to be of have its maximum frequency, this T on and T off must be equal. The TS is given by T on plus TF. Therefore, TS must be equal to tau plus tau, which is nothing but 2F, and Fs is given by 1 by TS. Okay, therefore Fs equal to 1 divided by 2 tau. Is it clear? Is it clear, ba? Okay, that is the thing we have used here. F max equal to 1 divided by 2 tau. Okay, since we have said that whenever T on and T off has same duration, the frequency will be maximum. Therefore, instead of S, I have used max notation. F max equal to 1 divided by 2 tau. Okay, and next is the bandwidth. Okay, what is meant by bandwidth? Bandwidth is nothing but a frequency component that is required by an communication channel to transmit the entire pulse signal. Okay, and if the maximum, as we have already noted that if the signal has 10 hertz as its maximum frequency component, the bandwidth of the channel must be greater than 10 hertz. Okay, so that only the signal can be transmitted through that channel. புரிஞ்சுதாப்பா? இப்போ ஒரு சிக்னல் வந்து அதோட மேக்ஸிமம் ஃப்ரீக்வன்சி காம்பனன்ட் வந்து 10 ஹெர்ட்ஸ் இருந்தது அப்படின்னா எந்த சேனல் வழியில் நம்ம டிரான்ஸ்மிட் பண்றோமோ அதோட பேண்ட்வித் என்னவா இருக்கணும்? அந்த 10 ஹெர்ட்ஸை விட அதிகமா இருந்தால் தான் அந்த சிக்னல் டிரான்ஸ்மிட் பண்ண முடியும். ஓகே, we can say another example. If a weighing machine has 5 kg, okay, but if we need to weigh some 10 kg, is it possible to weigh that machine which weighs only 5 kg? Is it possible? A weighing machine has a capacity or capability to weigh only 5 kg. Okay, but we need to weigh 10 kg. Is it possible? No, it's not possible. But reverse is possible. If a weighing machine has a capacity of 10 kg, it is possible to weigh 5 kg. Am I right?
Yes, sir.
Yeah, that total weighing capacity of a machine is denoted as bandwidth. Okay, and F max is nothing but actually what we are going to weigh. Therefore, that weighing capacity of a machine must be greater than the actual weight what we are going to measure. Am I right?
Yes,
10 must be greater than or equal to 5. reverse is not possible. 5 will not be greater than 10. We can't weigh a 10 kg with a 5 kg machine. Okay. Therefore, bandwidth must be always greater than or equal to maximum frequency component that is present in the signal. Okay. Therefore, BT must be greater than or equal to F max. Okay. F max is nothing but maximum frequency component that is present in the signal. Okay. Then here in the previous step, we have obtained the expression for F max, that is 1 divided by 2 tau. We are applying 1 divided by 2 tau for F max. Okay. Then bandwidth must be greater than or equal to 1 divided by 2 tau. And we know the value of tau. Tau is nothing but on time. Okay. Tau is nothing but on time. Here we have here we know that tau will be lesser than or equal to Ts. Therefore, here the symbol gets changes. Okay. Here we are combinedly using these two expressions. Here we know that bandwidth must be greater than or equal to 1 divided by 2 tau. We know that tau will be lesser than that of Ts. So we are applying Ts value, and it will be bandwidth must be very greater than that of 1 divided by 2 tau. Okay. Am I clear? Okay. We are using these two expression combinedly here. Okay. Instead of here, we know that tau, or we can write like this. Tau sorry. Is it clear now? Okay, here tau is less than Ts. Okay, we know that the on time of pulse must be very lesser than that of total time period of a pulse. And here we know the Ts value as 1 divided by 2 Fm. We have substituted 1 divided by 2 Fm. Okay, tau must be very less than 1 divided by 2 Fm. And here we have substituted the value of tau as 1 divided by 2 Fm. Okay, since it is very less, it must be bandwidth must be very greater than. Okay, and here 2 and 2 will get cancelled, and this Fm can be brought to the numerator. Therefore, bandwidth of a PAM must be very greater than that of frequency component that is present in the message signal. Okay, this is the primary condition, that is the to transmit an PAM signal, the bandwidth of the communication channel must be very greater than that of frequency of message signal. Okay, is it clear? Do you understand the last step? Okay, instead of tau, we have substituted 1 divided by 2 Fm. 2 and 2 will get cancelled, and this Fm can be brought to the numerator. Therefore, bandwidth must be very greater than that of Fm. Okay, and the advantages of PAM, and the main advantage is the device that is required to generate or receive or demodulate the PAM signal is very simple. Okay, no complex devices involved in both the generation and detection process. Therefore, it can be easily generated and detected. Detected means demodulation. Okay, that is the meaning we have to consider here. Detected is nothing but demodulation. Okay, and other forms of modulation can be easily generated. Okay, in the next section we will be seeing pulse width modulation and pulse position modulation. Okay, and this pulse width modulation and pulse position modulation are generated from the PAM signal only, or we can say it in otherwise, to generate PPM and PWM signal. First, we need to generate, excuse me, PAM signal. Okay, without generating PAM signal, it is very difficult to generate PWM and PPM signal. Therefore, PAM forms the basis for PWM and PPM signal. Okay, those are the advantages of PAM signal. And next is disadvantage. Okay, from the transmission bandwidth slide itself, it is clear that the bandwidth of a signal must be very greater than that of FM. In case of amplitude modulation, in the first unit we have studied, the bandwidth must be equal to twice the message signal. Okay, that is very simple. If the message signal has a 10 kilohertz frequency, the bandwidth of the communication channel has to be enough of 20 kilohertz. But here the bandwidth must be very higher than that of message signal frequency. Therefore, to transmit a PAM signal, we need higher bandwidth. Okay, that is the main disadvantage of PAM signal. And noise can be easily affected, as we have seen the first unit. Amplitude modulation can be easily affected by the noise. Likewise, pulse amplitude modulation is also can be easily affected by the noise. And high power requirement. Okay, high power requirement is nothing but, as I have told, that whenever the circuit is on, okay, it consumes more power. Okay, and when the signal voltage is 3 volt, it consumes some amount of power. Or we can easily relate, the power of a signal is directly proportional to the square of the voltage. Okay, do you understand? The power is given by V square divided by R. I think you might have studied that in the first unit. Power is given by V square by R. It is directly proportional to the voltage square. Okay, in case of pulse amplitude modulation, here the amplitude of the pulse gets increases. Okay, therefore the total power also increases, because if the pulse is 5 volt, let us assume R as 5 ohm and pulse equal to 5 square divided by 5, you will get 5 volt as the 5 watt as the power. If the amplitude of the pulse is increased to 8 volt because of pulse amplitude modulation, from 5 volt the amplitude is increases to 8 volt. Therefore, total power is given by 8 square divided by 5, which means 40 divided by 5, you will get 8 watt. Okay, instead of recovering 5 watt, it consumes 8 watt in case of pulse amplitude modulation. Is it clear? Is it clear, Pa? Without modulation, let us assume the amplitude of the pulse is 5 volt. Okay, and resistor is constant. Let's have a resistance value as 5 ohm. Power is given by V square divided by R. Therefore, power of an unmodulated pulse is given by 5 square, because voltage is 5. Therefore, 5 square divided by R value is also 5. 5 square value is 25. 25 divided by 5, you will get the power result as 5 watt. Okay, because of amplitude modulation, pulse amplitude modulation, the amplitude gets increases to 8 volt. Okay, and here the amplitude is increasing now from 5 volt. It may start increasing to some other value. Let us assume this value is 8 volt. Therefore, power is given by voltage square by R, which is nothing but 8 square by R. 8 square is nothing but 64, sorry, 64 divided by 5. 64 divided by 5 is nothing but, you will get nearly 13 volt. Okay, 13 watt. Okay, to carry an unmodulated pulse, it requires only 5 watt. But for a pulse amplitude modulated wave, we need approximately 3 times the power required to transmit an unmodulated pulse. Okay, therefore, pulse amplitude modulation requires high power. Okay, is it clear? These are the disadvantages of PAM wave. Okay, next is a pulse width modulation. Okay, pulse width modulation is nothing but, in case of pulse amplitude modulation, the amplitude of the pulse gets changes. Here, in case of pulse width modulation, width of the pulse gets varies. Okay, in the first class itself, I have shown the comparison. Okay, here instead of changing the amplitude, okay, here the amplitude of the pulse remains constant, but width of a pulse gets changes, which means the on and off time of a pulse gets varied with respect to the message signal. Okay, when the amplitude of the message signal increases, width of the pulse gets increases. When the amplitude of the message signal gets decreases, the width of the on time of a pulse gets decreases. That is pulse width modulation. Okay, that is the thing that can be generated with this basic block diagram. Okay, in PWM system, the message signal are used to vary the duration. Duration is nothing but on time and off time. Okay, duration of the carrier pulse. The message signal may vary either trailing edge or leading edge or both the carrier pulses. Trailing edge or leading edge means transition from 1 to 0. Okay, that is the trailing edge because it decreases. That is given by trailing edge. Leading is given by leading is the just denotes transition from 0 to 1. Okay, it may change based on our requirement. We can increase the on time or we can change the off time. Okay, based on our requirement, we can alter the on time or off time of a pulse. Okay, and width of the pulse is proportional to the amplitude of the message signal, as I have already told that this change occurs based on the message signal's amplitude. Okay, and here the amplitude and the position of the pulse remains unchanged. Okay, that is the most important thing you have to be noted. The amplitude and position of the pulse remains unchanged in pulse width modulation. In case of pulse position modulation, the amplitude and width remains same, but position of the pulse gets changes. Okay, this same logical diagram or this same modulator can be used for generating both PWM and PPM signal. Okay, PWM and PPM signal are generated in a single device. Okay, and the functionality of this device is very simple. First, we need to generate a PAM signal. Okay, from the analog input signal with the basic multiplier, we are generating a PAM signal. As I have already told that PAM forms the basis for other types of modulation techniques. Okay, to generate PAM and PWM, we need to generate PAM priorly. Okay, and this instantaneously sampled PAM generator is nothing but a basic balanced modulator what we have used in the previous modulation technique. This modulation technique is used for PWM and PPM generation. The output of this PAM generator is a PAM signal, and here we are using a sum operator. Okay, which means a device which performs the addition of both the inputs. Okay, the output of this device is nothing but a summation of both the inputs, and here we are using a comparator. The basic function of a comparator is to compare both the input. Okay, here we are providing both the input, and based on the inputs it produces an output. Okay, by comparing both the input produces the output. Okay, and this output can be used for generating PPM signal, that is pulse position modulation. It will be very clear when I am explaining with the diagrammatic representation. Okay, and just understand the basic functionality of the block here, and in the next slide I will be explaining the how PPM and PWM get generated. Okay, first we are having a PAM generator. It generates the PAM signal, and the output of PAM generator is given to the summation device. It performs the summation between PAM signal, that is the output of a PAM generator, and a triangle wave generator. Okay, this triangle junction generator is nothing but a triangle wave generator. Here we are using a triangle reference signal for finding the or for obtaining the PWM and PPM signal. And comparator is nothing but a device that performs the comparison operation between both the input and produces the output. And with PPM, it is possible to generate PEM signal by using a monostable multi-vibrator. Okay, this is the basic functionality of this PWM and PPM modulator. If they are asked to write the to explain about the PPM modulator, means you can draw the same diagram and you can explain the same building blocks. Okay, and it is the PWM PPM generation process, and please listen carefully because it is the most important thing. With this only you can able to explain the logical operation that happens behind building blocks. Okay, and if you have any doubt, please let me know. Okay, இது ரொம்ப முக்கியம்ப்பா. இதை வச்சு தான் நீங்க இந்த கொஸ்டின்கான ப்ரீவியஸ் கொஸ்டின்கான ஆன்சரே எழுத போறீங்க. நீங்க இந்த பிளாக் டயக்ராமுக்கான ஆன்சரேவும் இந்த டயக்ராம் வச்சு தான் எக்ஸ்பிளைன் பண்ணணும். ஸோ ப்ளீஸ் லிசன் கேர்ஃபுல்லி. ஓகே, here we are having a PAM signal. PAM signal is nothing but a signal in which the amplitude of the pulse gets changes. Okay, and the output of PAM generator is given as the first signal. Okay, and PAM is the signal in which the amplitude gets changes. Here the amplitude gets changes. The amplitude of the pulse is not uniform. Therefore, we can call this as PAM signal. And next is a triangle signal. It is a reference signal what we are generated using the triangle junction generator. Okay, with the help of an oscillator, it is possible to generate a triangle wave. Okay, then next the output of summation. Okay, here we are just providing the PAM signal and triangle signal to a summation device. It just performs the addition operation between the amplitude of the both the signal. Okay, and the amplitude of a PAM signal and triangle wave gets added. Okay, just compare both the signal, just or compare all the three signals. It is possible to understand this third signal. Okay, just the amplitude of both the signal gets added. Here PAM signal has higher amplitude, therefore this pulse has higher amplitude. But here in this pulse the amplitude is very low, therefore here we are getting a low voltage at the output of a summation device. Is it possible to understand the third signal? Third signal eppadi vandadhu purinjadappa? Just we are summing the output of PAM generator and the triangle wave generator. Okay, and here a reference signal is provided. Okay, this reference signal is generated based on the previous output. The function of this feedback is will be explained later. Okay, just consider here we are providing a reference signal. எதுக்காக இந்த அவுட்புட்டே எடுத்து ரெஃபரன்ஸ் கொடுக்கணும் அப்படின்றத I will explain later. Okay, just consider here a reference signal is provided and this reference is nothing but VR. Okay, and here just assume here reference signal may be 3 volt or 5 volt or 8 volt. Okay, and just we are clipping of the signal which lies above the or which lies below the reference signal. Okay, here let us assume this is a VR, this is the reference signal, and here a pulse, the signal voltage which lies below the reference signal, and here just note it down. Up to this, here we are having voltage level that is higher than that of reference signal. Reference signal viட அதிகமா இருக்குல இந்த இடத்துல voltage. So we are considering that duration to create a pulse, and we are just omitting the signal level which has voltages lesser than that of reference. Okay, and with this you can able to write the working functionality of comparator. Okay, comparator just compares the output of summation device, this signal, and a reference voltage. Okay, it just provides the output whenever the output of summation, that is whenever the output of positive input is higher than that of negative input. Okay, is it clear? We are providing two input. One input is given to the one input is denoted as plus and other input is denoted as negative, just for our understanding. Okay, and whenever the output of summation device or the input of positive pin of a comparator is higher than that of reference voltage, or the voltage that is applied at the negative end is higher, we are getting the output. Okay, comparator function என்னப்பா, ரெண்டுமே கம்பேர் பண்ணும். ஒன்னு கிரேட்டரா இருந்ததுன்னா அவுட்புட் கொடுக்கும், ஒன்னு லெஸ்ஸா இருந்ததுன்னா லெஸ்ஸர் அவுட்புட் கொடுக்காது. அதுதான் comparator பேசிக் ஃபங்க்ஷன். We are comparing both the input, and whenever one signal voltage is higher than that of other, comparator provides the output. Okay, and here up to this, by comparing this both the signal, that is VR is one signal and this pulse is another signal. We are comparing both the signal. Whenever the voltage of this signal is higher than that of reference signal, it produces an output. Okay, whenever the voltage signal of a PAM signal is lesser than that of reference voltage, it doesn't produce any output. Puridapa? Up to this period, voltage level is higher than that of reference voltage, therefore a pulse is produced. And note it in the second pulse here, up to this position, voltage is higher than that of reference voltage, therefore a pulse is produced. And in this signal, up to this only, voltage level is higher than that of reference voltage, therefore pulse is produced for that particular duration. Okay, with this, the width of the pulse is varied. Okay, pulse oda width maruda, because in the rendoda amplitude summation maarappo automatically reference voltage la irundhu clip agara voltage maarum, therefore the width of the pulse gets changes. Okay, is it understandable? Is it understandable? Just whenever the amplitude of the pulse gets higher than that of a reference voltage, a pulse is created, else pulse will not be created. Okay, it is the output of PWM, and here we are getting output with the varied pulse width. Therefore, we can call that as a pulse width modulated wave. Okay, the next one is a PPPM. PPM is nothing but pulse position modulator, and here pulse position modulator is nothing but it. Here we are using a monostable multivibrator. Okay, the function of this monostable multivibrator is to trigger a pulse, or it will create a pulse whenever a trailing edge occurs or a leading edge occurs. Okay, based on our requirement, we can make the monostable multivibrator to trigger for a trailing edge or a leading edge. Okay, here we are triggering the monostable multivibrator for a trailing edge. That is, we are making a monostable multivibrator, or we are making the device to create a pulse whenever a transition occurs from positive to negative, or whenever a transition occurs from leading edge to trailing edge, or on to off. Okay, whenever a pulse changes from on time to off time, a pulse will be generated. Okay, here on to off, a pulse is generated, and here to a pulse will be generated, here to a pulse is generated. Just consider position of the pulse gets changes. Okay, compare this, it is the position of a basic pulse. Okay, but consider this, the position gets changes. Okay, instead of having a pulse at this point, we are having pulse at the some other location. Therefore, the position of the pulse gets changes. We got pulse position modulated wave. Is it clear? Am I still in the meeting?
Yes, sir.
Yeah.
Yes,
Is
sir.
it clear for you?
Yes, sir.
How the
Yes.
PBM and PWM signal gets generated? For PWM, we are just comparing the output of a summation device and a reference voltage. Whenever our pulse is higher than that of reference voltage, pulse will be generated. Or for the duration up to which our pulse is higher than that of reference voltage, a pulse is generated. Okay, and for a pulse position modulated wave, whenever a transition from off on to off, a pulse is generated, a pulse of constant width is generated. Here this pulse is generated by this multivibrator device. Okay, in this device it is possible to adjust the width of the pulse. Okay, and if we need to generate a pulse of the original width, we can generate. Okay, for our understanding, they have given a pulse width has smaller width. Okay, we can change the width of the pulse based on our requirement. Just you need to understand here the position of the pulse gets changes. Instead of here, we are getting a pulse at this location. Okay, therefore based on the message signal, the position of the pulse gets changes. Okay, here you can ask one question. Here we are not denoting any message signal. Message signal inga kudukave illa, but we are saying the width of the pulse gets changes with the message signal, or position of the pulse gets changes with the message signal. First, you need to understand that this PAM signal is generated with message signal only. Okay, the amplitude of the pulse gets changes with the message signal only. Therefore, if any other signal changes with respect to this signal, then it corresponds to the message signal also. Okay, this pulse amplitude modulated signal is generated with the help of message signal only. Okay, and this PWM and PPM is created with this PAM signal. Therefore, this PWM and PPM is also created with the message signal only. Okay, is it clear? Is it clear for you?
Sir. Yes, sir.
Okay. With this, we are completing the second part of first part of second unit. Okay. In the next class, let's once again see the overview of all the three modulation technique, and let's get into the second part of second unit. Okay, second part is very simple, and it will be what you have studied in the communication, what computer communication, like bits. You might have studied in the 12th standard if you have chosen the computer science as a subject, like floating point number, ASCII code, error reduction code, parity bit, gray code. It will be like that only. That is very simple, and it will be very simpler than the rough first part. Okay. Okay, with this, let's complete the first part of second unit. Let's take the attendance. Okay, is it clear? புரிஞ்சுதாப்பா இல்ல ஏதாவது டவுட் ஏதாவது இருக்கா?
Yes, sir. Clear,
Yes,
sir.
sir.
Okay, okay, thank you, thank you. Let's take the attendance. And unit test எல்லாம் சப்மிட் பண்ணிட்டீங்களா? யாரா சப்மிட் பண்ணாம இருக்கீங்களா யூனிட் டெஸ்ட்? சப்மிட் பண்ணிட்டீங்க. ஓகே, குட். ஓகே, இன்னைக்கு நான் பேசின இங்கிலீஷ் புரிஞ்சுதாப்பா?
Yes, sir.
ஏதோ புதுசா
Yes,
ட்ரை
sir.
பண்ணலாம்னு இங்கிலீஷ்லயே கிளாஸ் எடுத்தோம், புரிஞ்சுதா?
Yes,
Yes,
sir.
sir.
ஓகே 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 கண்ணா. Then shall we continue like this? இதே மாதிரி கண்டினியூ பண்ணலாமா?
Okay, sir.
Yes, sir. Continue, sir.
ஓகே கண்ணா, thank you, thank you. Answer your attendance. Abhinav,
Present, sir.
Abhirami,
Present, sir.
Gita,
Present, sir.
Arunachalam,
Present, sir.
Ashifa,
Present, sir.
Ashwin, Ashwin, Bhavishni,
Present, sir.
Daski,
Present, sir.
Arnidharan,
Present, sir.
Deenadarshan, Dhanashiva,
Present, sir.
Nagaran,
Present, sir.
Dinesh,
Present, sir.
Adimiran,
Present, sir.
Manasekaran,
Present, sir.
Gokul,
Present, sir.
Gokul Das,
Present, sir.
Hariharasudan, Hariharasudan,
Sir, Hariharasudan, present, sir. Present, sir.
Hariharan,
Present, sir.
Harikrishna,
Present, sir.
Chandrasekharan,
Present, sir.
Jagadish, Janani,
Present, sir.
Jayasuriya,
Present, sir.
Jyoti, Jyoti, Karan, Karan, கேக்குதா கேக்கலையாப்பா?
Sir, present, sir. கேக்குதா, sir?
ஓகே, கார்த்திபன்,
Hello.
கார்த்திபன்,
Present, sir. Hello. Present, sir. Present.
ஓகே, கரண் ஓகேப்பா, கரண் ஓகே. கார்த்திகேயன்,
Present, sir.
கவியரசன்,
Sir, Jyoti, present, sir.
ஓகே கண்ணா, ஜோதி ஓகே.
Present, sir.
காவியதர்ஷினி,
Present, sir.
லோகேஷ்,
Present, sir.
மகேஷ் குமார், மகேஷ் குமார் இல்லைங்களா? மாருதி அர்ஷத்,
Present, sir.
முசாகிர்,
Present, sir.
மோனிகா,
Present.
முத்துராஜ்,
Present, sir.
ரகுபதி,
Present, sir.
பிரியங்கா,
Present, sir.
ரகுராம், ரித்திஷா,
Present, sir.
ரோஷன், கவிதா,
Present, sir.
ஓகே, சந்தீப் குமார்,
Present, sir.
சந்தோஷ்,
Present, sir.
ஏன் சந்தீப் நீங்க காலையில டெஸ்ட் எழுதல, யூனிட் டெஸ்ட் எழுதலையா?
Present, sir.
ஓகே, ரோஷன் ஓகேடா, பிரசன்ட் போட்டேன் நானு. சரவணன்,
Present, sir.
சதீஷ்குமார், சண்முகப்பிரியன்,
Present, sir.
சண்முகவேல், சண்முகவேல் இல்லையா? ஸ்ரீராம்,
Present, sir.
சுபாஷ் சந்திரபோஸ்,
Present, sir.
ஆரிக் ஜமால்,
Present, sir.
விஷால்.
Present, sir.
ஓகே, சந்தீப் நீங்க காலையில டெஸ்ட் எழுதலையா?
சார் ஹரிஹரன்
சந்தீப்.
பிரசன்ட் போட்டீங்களா சார்?
ஹரிஹரன் போட்டேன் நானு. சந்தீப்
Sir, Hariharan present, sir.
ஏன்டா எழுதல? ஓகே, ஹரிஹர சுதன் பிரசன்ட் போட்டாச்சுப்பா. ஓகே, சந்தீப் மட்டும் இருங்க, மத்தவங்க கிளம்பிக்கலாம்ப்பா. தேங்க்யூப்பா, தேங்க்யூ. மண்டே மீட் பண்ணலாம். தேங்க்யூ.
Thank you, sir. Okay, sir.
தேங்க்யூப்பா, தேங்க்யூ.
Thank you, sir.
தேங்க்யூ.
Sir.
சந்தீப் சொல்லுங்க சந்தீப், ஏன் எழுதல?
Sir, Ashwin Krishna present, sir.
என்னோட நம்பருக்கு நீங்க கால் பண்ணுங்க. சந்தீப் என்னோட நம்பருக்கு கால் பண்ணுங்க.
Okay. Sir.
ஓகே, சொல்லுங்க ஹரிகிருஷ்ணா.
Present, sir.
போட்டுங்க, நான் பிரசன்ட் போட்டேன்.
Okay, sir.
ஓகே. தேங்க்யூ.
Thank you, sir.